Hello, and welcome to Chapter 3, Section 1. So today, we are done with Chapter 2. So Chapter 2 was the whole chapter about finding derivatives. In this chapter, Chapter 3, we are trying to use what we know about finding derivatives and applying them to, other things. So, in this chapter, our goal right now is to be able to do something, what we call a curve sketching. So, if I were to give you any equation, to actually figure out all the different important features of the graph without actually having to plot every single point and on a graph. So sketching. So curve sketching is what we're trying to do in order to build up to that, because we won't get to that point until chapter or section 5. In order to get up to that point, we need to learn how to find different little parts, pieces of our graph so that we can get to this curve sketching thing. So in this first section, we are looking for extrema on an interval. So extrema, you might have heard the word before, it sounds like extremes. So basically, they're like maximums, minimums, which you definitely have heard before, because when we talked about parabolas way back in the day, the maximums were and minimums were the topmost point or the bottommost point of the U. And then we had those as well for absolute value graphs because it made a V. So now we're talking about extrema, meaning it's not just going to be a parabola. There might be more squiggles in between our graph. And so any of those points where it kind of makes that hump either on the top or the bottom, they all count as minimums and maximums, just, relative to the overall curve or the graph. So overall, they're called extrema, like extremes, but extrema. And then if we look specifically at an interval of numbers, so what x values do we want to look at, that's the interval that we're talking about. So we're going to be able to identify those extrema given an interval. So first I want to talk about the extreme value theorem. So this theorem is to me, it sounds very obvious, but all it's saying is, let's say we're looking at the interval from A to B, so two numbers, x values, A to B. Whatever the graph looks like between those two x values, it's going to have a minimum and a maximum, and it has to have both. And what it's saying there is just that, when we talk about a minimum or a maximum, we're talking about y values, so how high up does it go, how low does it go. So in that interval, we're saying there's going to be a tallest point somewhere and there's going to be the lowest point somewhere. It doesn't matter if it's actually the bottom of a U or the minimums and maximums that we were talking about before, the extrema. This is just literally saying what is the highest and lowest y value. That's all it's asking for. So let's say we had this graph, f of x, and we're looking at x values between A and B. So I'm just going to call these 2 points, A and B. So we're looking for a minimum and a maximum within this interval. So in between A and B, there's got to be a highest point and a lowest point. So just by looking at it, it should be pretty easy to see. So the highest point should be right here. So that would be the maximum. The lowest point, looks like the lowest it goes, is right here, which is different than what we're kind of used to, because we're thinking of maximums and minimums where it changes where the hump is basically, because right here is probably really where the minimum is, but that's not within the interval from A to B, so that doesn't count. So that's why our 2 points would be right here and right here. So when we're being asked to identify the maximum or minimum values, then we're just looking at the y values of those points. So another thing I want to talk about then is the relative maximum and minimum, and this is what we are used to. So relative maximum and minimum occurs on the humps of the graph. So in the same graph that I have, I've got 3 relative extrema. So extrema just kind of talks about maximums and minimums overall. So here I've got a relative maximum here, another one over here, and a relative minimum here. So again, just the top or bottom most points of the humps. One other thing is an absolute maximum or minimum. So absolute means over the entire graph, what is the highest and lowest points? So in this graph, the very highest point that this graph reaches is this one right here, because yeah, it's a little bit taller than my other relative maximum. However, this graph does not have an absolute minimum. We had a relative minimum here, but if you look at like the graph itself on the ends, they do technically keep going downwards like this. So if they keep going downwards forever and ever and ever, because that's what the arrows mean, then this doesn't end up being the lowest point. So there is no absolute minimum, just an absolute maximum, because there's nothing, the graph's not going to go any higher than this. Okay, another thing that I want you to notice with relative minimums and maximums is that if we were to draw a tangent line that passes through those points, the tangent line would kind of go across like this. So remember, tangent line is where it's a line that only touches the graph once, so at a single point. So at like the peak of the graphs, that tangent line would be horizontal so that it only touches at that one point. And that's special about our relative minimums and maximums. The tangent line has to have a slope of 0 in order for it to be a tangent line at any relative maximum or minimum. Which brings me to my next point, and probably the most important for this section, critical points. I know, important, critical, I know. So critical points is the x values where the derivative equals 0 or the derivative does not exist at all. So if you think back a little bit to chapter 2 when we talked about derivatives, the derivative does not exist when the function's not continuous, when you have any sharp turns, or if you have a vertical tangent line. So if your graph, your function has any of those things, the place where it occurs, the x value where it occurs, would count as a critical point. And also, when you can set the derivative equal to 0 and solve for x, that'll also count as a critical point. And these critical points are important for us because they help us solve for other things later on. All right, so let's do an example together. We're going to find the extrema on the interval from -1 to 2 on the function f of x equals 3x to the 4th minus 4x cubed. Okay, so in order to find the extrema, they give us an interval, so we know what the endpoints are going to be of our interval. We need to figure out if we have any relative minimums or maximums within the interval so that we can see if those would be the extrema. So first, we're going to find the derivative and set it equal to 0, because that's how we can figure out our critical points. Looking at the function itself, I also have, it's a polynomial function like 3x to the 4th minus 4x cubed. So knowing that, anything x to the 4th or any polynomial function, the graph is just going to be like a bunch of wiggles. I'm not like super worried about like what the overall graph is going to look like, but you want to know basically if there's any vertical tangent lines, which in a polynomial function there is not. So we're not worried about that here. So our critical points are just going to be where the derivative equals 0 then. So the derivative we can find easily is just going to be using our power rule on 12x cubed minus 12x squared. Okay, not too bad. So we want to set this derivative equal to 0 in order to find our critical points. So setting this equal to 0, I need to solve for x. The easiest way here would probably be to factor, because there's a greatest common factor of 12 squared. And if I factor out a 12x squared out of both terms, I end up with x minus 1. Okay, and then just solve for x from here. So with the 12x squared, I can set that equal to 0, and I end up with x equals 0. With the x minus 1, setting that equal to 0, I get x equals 1. So those are my two critical points. Cool. So then we also need to look at whether our endpoints might be, the endpoints of the interval might be minimums or maximums as well. So what I'm going to do, to me the easiest, most organized way to do this is to make a little XY chart. Because now I know my critical points were at 0 and 1, so they're probably either minimums or maximums. And then my endpoints were -1 and 2. Oh, one thing I forgot to mention. When you solve for x, you also want to make sure that these two values are within the actual interval that they give you. If they're not, then it wouldn't count because we're only looking at x values between -1 and 2. Okay, so we have our two critical points. We are also looking at our endpoints. We don't have any spots on our graph where the derivative doesn't exist. So that's it for our critical points. So basically when you make your XY chart, you want to just include critical points and the endpoints. we want to figure out the highest and lowest y value for minimums and maximums. So we're going to plug all our points, our critical points and our endpoints into our original function, original equation, to find our y values. And then we would just look at all our y values, see which one's the highest, which one's the lowest, and that'll tell us our min and our max. So plugging in 0 into my original function, I get 0. Plugging in 1, I get -1. Plugging in -1, I get 3 minus 4 times -1 is 7. And plugging in 2, mental math, here we go. 48 minus 32, 16? Hopefully I did that right. Okay, so now I have all the y values. Just looking at them, I just need to figure out which one's my highest, which one's my lowest. So I know my numbers. So the highest would be an x value of 2, y value of 16. And then my lowest y value is the -1 when x equals 1. So I end up with a minimum of -1 at x equals 1, maximum of 16 at x equals 2. There we go, I've identified it. Okay, so let's do another example together. This time I am looking at the interval from -1 to 3, and the function is 2x minus 3x to the 2/3 power. So again, I'm going to find my critical points by setting my derivative equal to 0, and I also want to look for any points where the derivative does not exist. So just looking at my function right now, it's not a polynomial function because I have this x to the 2/3 power. So 2/3 power, if you think about it, is really like a cube root function that's also being squared. But the cube root function, like in general, does have a vertical tangent line, because a cube root function, I really quickly sketch it out, looks something like this. It's that weird like squiggle thing. And right here in the middle is a vertical tangent line. Because the only way that you can get a point to pass through only one time is with a vertical tangent line there. So in a cube root function, the point where that occurs, the vertical tangent line occurs, is where the cube root, the stuff you're taking the cube root of, is going to equal 0. So for us, our function, if I rewrite this, is like, oh, that's a minus sign, not an equals, 2x minus 3 times the cube root of x squared, if we were to rewrite the 2/3 as a radical instead. So the inside of my cube root would equal 0 when x equals 0. So that means at x equals 0, we have a vertical tangent line, which means x equals 0 is a critical point. Okay, so finding the rest of my critical points now, I want to set the derivative equal to 0. So the derivative of this function is going to be 2 minus 3 times 2/3 is 2x to the -1/3 power. And then I'm going to set that equal to 0. So solving for x now, I can add the 2x to the -1/3 power to both sides, and then divide both sides by 2. And then, so I don't really like my radicals like this. I'm just going to rewrite it so it looks nicer. All right. This, now I can just multiply both sides by the cube root of x and then cube everything. So in this case, I just get a critical value of x equals 1 and then the x equals 0 from before. So making my xy chart now, I have critical points at 0 and 1, and both of those numbers are between my interval from -1 to 3, so that means I'm keeping both of those, and then using my endpoints as well. So now plugging into my original function, 0 is going to be a y value of 0, plugging in 1. I just did the rest really quickly. With the x equals 3, I do end up with the decimal, which is fine. And again, once I have everything plugged in, we're just looking for the biggest and smallest numbers of all my y values. So I think the biggest is going to be 0. Wow. And the smallest is going to be at y equals -5. So that means I have a maximum of 0 at x equals 0 and a minimum of -5 at x equals -1. Cool. One more example to do with you guys, and then that's it. All right, this time I've got the function 2 sine x minus cosine of 2x. Throwing in some trig here. So think about the graph for sine and cosine. They're going to be like a wave. It goes up and down. They're continuous, differentiable everywhere. You can find the derivative everywhere. So really, our critical points then are just going to be where the derivative equals 0. So let's find those critical points. The derivative for 2 sine x is going to be 2 cosine x because 2 is a constant multiplier, and the derivative of sine is cosine. Then we have a minus. Cosine of 2x requires chain rule. So the derivative of the cosine would be negative sine, where the inside stays the same, but then we have to multiply that by the derivative of the inside, and the inside is 2x, so the derivative would be 2. So this ends up being 2 cosine x minus, plus, I got minus a negative, 2 sine 2x. And we're setting that equal to 0. All right, I know it's been a while since you've last solved trig equations, so here we go. First, my equation has 2 different trig functions in it. It has a cosine and a sine, so this isn't super helpful. What I can do, though, is because I have a sine of 2x, there is a trig identity that I can use to make this better. So I'm going to substitute in the trig identity for sine of 2x. I can rewrite that as 2 sine x cosine x. Then simplifying that out, I end up with 4 sine x cosine x. And from here, because I have cosine x in both of my terms, I can factor that out. Really, I'm just going to factor out a 2 cosine x, because then that'll leave me with 1 plus 2 sine x. Once I have things factored, that's the best way. I need to factor everything, and then I can just set each of my factors equal to 0, just like how I factored stuff out before. So 2 cosine x equals 0, and 1 plus 2 sine x equals 0. Solving from there, I'm basically going to divide both sides by 2. Cosine x equals 0 at, let's see, thinking of the unit circle, and 3 pi over 2 is where we're going to have cosine equal to 0 there. Okay, and then with my other equation, I can subtract both sides by 1 and then divide by 2. So sine equals negative 1/2 at 7 pi over 6 and 11 pi over 6. Okay. So lots of relative minimums and maximums here. It looks like all of my answers are within the interval from 0 to 2 pi, so I do have to test all of these, and the 0 and 2 pi for my endpoints. So after plugging in my x values into the original equation, these are the y values I got. The maximum, the biggest y value looks like this one, and the smallest are these two. So because I have 2 x values with the same y value, they're both the smallest, I'm just going to end up with 2 minimums here. So I'm going to have a maximum of 3 at x equals pi over 2 and minimums of negative 3 over 2 at both x equals 7 pi over 6 and 11 pi over 6. Okay, that's it. So for practice then, you want to be able to find critical points and then find extrema. Those are the 2 things you should be able to do in this section. Thanks for watching. Bye.